And stepped up to the plate for us.
Yeah, I noticed. So there was a confusion. Really, I sent an email. There was
Sent an email about the.
or an announcement. What is
You
that
posted
called?
an announcement on D2L.
Yeah, it was not.
There was an announcement on D2L, but the problem is
Oh, no one goes to
you
D2L.
don't go there because we don't normally, all our stuff is on your webpage.
Yeah. I understand that. I mean, okay, actually, so that's a confusion I have. I thought that when I send an announcement, it comes as an email to you.
Oh,
It actually doesn't. Now, emails will come through, but the announcements did.
Okay, because when I send an announcement, it comes to me. So I assume that it goes to everyone. So okay, that's now I understand. So that's my fault. Yeah.
And it could be something that we'd have to alter the settings.
Yeah, but no, I mean, I don't expect people to go to D2L. Like it's my website that I will, I prefer, or the way I have set the protocol in the class is that go to the course webpage. So that makes sense. Yeah. Because I thought everyone got the announcement. Why is everyone talking? It makes sense. Yeah.
I told everybody, I said, someone else needs to ask. He's still mad at me over homework too, so I'm not going to ask.
No, I see, these are the misunderstandings. I don't know that this happened, right? So I'm assuming that everyone got the email. Okay, I don't get this point. But in this class, we can avoid these kind of stuff. If the same situation happens in physics 205, 200 level, I'll probably not budge. I said, we are going doing this. So I'm more careful there. I don't make mistakes there. So I'm very careful there. Or I'm very intimidated, you can say. One word is careful, the other word is
sure. Also, there's probably an expectation from your students that they should look at D2L to see any.
Yeah, exactly. But these kind of mistakes can happen, right? I can make mistakes. Like I'm so strict, like the homework and quizzes come 5 minutes, 3 minutes late. I don't accept it.
Yeah.
So I feel I'm being very harsh. But if I relax it for one, there will be 5 or 6 coming up, and then I'll be just managing them.
Well, especially when you have larger classes.
Yeah. But again, it's a decision I take. I can always justify the way. So Jordan, you wrote for everyone. Thanks. I just got the information that the announcement that goes on D2L never reaches you guys as an email. I thought it goes as an email, so you guys didn't see it. Understandable. So I made it due all the way on Sunday. So, but you guys said it's for Thursday is good enough, but I thought I'll give you guys a weekend. But I'll also make the homework due on maybe Tuesday or something. If that's okay. Right.
That's fine. Yeah, I wrote it firstly for my own sanity because I had meetings basically all day yesterday. So, and Saturday I didn't see the email, I don't think, until Sunday.
So you did get an email?
No, I didn't see the email from Rob.
Oh, Rob.
Sent an email that said something
It was on there, but it was like Sunday or something like that.
Yeah. So,
Yeah.
and I had plans this weekend that my wife had made, so I wasn't even at my house able to work on it. So I would have had a few hours to try to look at it and finish it. So
No, it's okay. Yeah. I think some advantages when everyone seems to be working as much as they can in the class. This typically gets spoiled when there is one student who is not working, not doing anything, and then I have to control that student, everyone suffers. So these kind of relaxations, everything goes out of the window. But typically I notice that graduate classes are reasonably okay. So, okay. Good. So anything else? Again, so I should find this, write this out. So midterm one is due Sunday. Let me not say when it is so that don't go to the last moment. Homework. 4, I haven't posted yet, but this will be due March 2nd, I think so. I think I should be able to finish it up. Yeah. And this is going to be the content-wise that it will be very long, but that's because we're doing a circular wire. It will have a lot of results. But I ask you guys to do only a few of them, so there might be around 10 of them, but you have to do only. You have to fill in the steps only for about 3 or 4 of them. So this will be a different kind of homework. So you'll see a lot of it. So it look very overwhelming, but it's not. Or it might be also in between. So don't get overwhelmed, or that's what it is, right? But it's not. I think it's not. But do very little. Okay. I haven't opened it yet because I want to decide which ones I want you guys to do. Okay. Anything else? We're missing some, right? Oh no, because you're here. Or is there anyone else? 1, 2, 3, 4, 6. Yeah, more of us. Yeah. Typically they're smaller, I guess, because Luke is up there. Okay. So we said we wanted to work on find the vector potential and magnetic field due to a circular wire, and in that, for as a warm-up for that, we started working on elliptic integrals. So we wanted a little bit more on elliptic integrals, but very little, and then we'll come back to. So today itself in half an hour or so, we should be able to come back to the wire. So let me remind you. So this is a complete elliptic integrals. Now, the first kind, so there's a first kind and a second kind. First kind is k of k, so that's a function capital K, variable is small k, it's from 0 to pi by 2 d theta, and this is 1 minus k squared sine squared theta. The complete elliptical integral means that it is going all the way to 0 to pi by 2. If you stop it at 0 to some x, let's say, then it is a function of 2 variables, k and x, and that's what is called an incomplete elliptic integral. The second kind is e of k, and that's 0 to pi by 2 theta. And we motivated saying that this is this shows up when you're doing the circumference of an ellipse. And did I motivate this at all? Probably not, right? Did I mention it at least?
Yeah.
So
did you mention what? I'm missing.
did I mention in what context do you see the first kind? You see it in various places, at least one place where you see a complete elliptical integral of the first kind is a pendulum with no small angle approximation. And that might be one of your homeworks where you show that. It's reasonably easy. Once you accept this, there's not much to do. That's the same thing we will see for the wire also, circular wire. You cannot do the integral, so you just have to show that this is a elliptic integral, that's all. It's more of algebra transforming from the expression you have into identifying in what kind of function it is. So that's what mostly it happens. And the same thing you have to do in pendulum. From the expression that you get, you have to show that this is actually an elliptic interval. And what I feel is nice about that example is often we should ask ourselves, whenever there is an approximation made, we should know how much error we are making. Right? And we always say that small angle approximation, we don't make much error, but how much is small angle is how much is small angle? Like is 60 degrees small angle?
I think it was like 20%, 20% or less.
Yeah, exactly. So you have to talk about percentages then. So how much error do you make? And what you will see is that even for 60 degrees, we don't make much error. It's remarkable how accurate these things are. And that will be one of the questions as to how much error do you make in for 60 degrees. 60 degrees is about 1 radian, and it is less than 10%. So exact value you will calculate. And for 30%, it comes down to very low error. That's remarkable in that sense. Yes.
There was an example that doesn't use the elliptical integral, but in I think it's Stairway's physics, the intro to physics. They do Snell's law without the sign.
Oh, without the sign. And if it is 10 degrees, it will come out.
N1 theta 1, and it's actually surprisingly accurate.
Wow, yeah, because 10 degrees is almost the same. Yeah, I see it. But if you go probably 60 degrees, maybe.
Oh, yes.
Right. Yeah.
I had them one time do a comparison.
That's nice. Yeah.
And but the first time I saw it, I thought, well, this is ridiculous. And then I said, that's actually not bad.
No, good point. Yeah, exactly. Snell's law, fine theta. Yeah, didn't strike me. Very good. Good example. There. And actually, this is maybe I'll give a quiz related to this. So it suddenly strikes me. This was something. There was a high school student who wanted to do a project. So the project we gave was to make a pendulum which is exact. Like so, usually you have a pendulum which is dependent on the amplitude, right? Its time period depends on the amplitude. Is that clear what I said? Mm-hmm. So the time period of a pendulum depends on the amplitude. The larger the amplitude, time period changes, it increases, I suppose. But now there was in 1600s itself, Huygens, I don't know how you spell it, Huygens. How do you spell this? Huygens, Huygens. Yeah. Anyway, he came up with a design for a pendulum which does not actually depend on this amplitude. So always it will be T. Like the standard result that we have, T is equal to 2 pi times L over G. Right? This has corrections in general. Right? If you do a normal pendulum, this is 1 plus, at least this is phi naught square. I think it's on 16 something. Like there are corrections to that. But, so this is a simple pendulum. Standard simple pendulum. But there is this, what is called cycloidal pendulum, invented by Huygens. Cycloidal. Where T is just always for all amplitudes. It is this remarkable. How do you do this? There was a student who worked on it and he made a video. Young, 8th grade student, and they're pretty good at making these videos. They did a pretty good job actually. But what you do is, what's a cycloid to begin with? Am I in the screen? So the quiz is to find out about cycloid. So what is a cycloid? Anyone? What is cycloid? You should know. want to.
I'm just guessing it's maybe a circular.
Is that the shape that has the little, like,
You're almost telling it.
you're in polar coordinates, and I can't remember the equation for it.
Yeah, don't remember the equation. Think of how do you simulate it?
Trace out by
Trace out by?
circle rolling.
Yes, that's correct.
Okay.
Circle rolling, a bicycle. Like if you put a LED light on your bicycle wheel at the outer rim, and in the night, if you were to drive the bicycle, the LED will take the path of a cycle. Is that clear? Those online? I think you cannot see my movements of hand probably.
Yeah.
So the
like
point is,
a
so
rolling-
think of a circle. This is a wheel of a bicycle. This is rolling with constant angular speed, and let's say you have this LED light stuck on that, and it will actually take a path. This is not a part of a circle. This is so that path is called a cycloid. Okay, reasonable.
How is that related to like the brachistochrone thing where you know, the
Yes, brachistochrone solution is also a cycloid. If you were to ask what is so I think brachistochrone is you drop something from here and you have to reach here. If you go along a straight line, it takes more time. There is a path that actually makes it. That's part of a cycloid. If you were to complete this, that's a cycloid. So PHYS, the idea was, or cleverness was, very brilliant kind of known. At least it's hard to think of how he came up with it. So have a pendulum. Now first have so the student I'm talking about, he 3D printed the cycloid. So I had a 3D printed, so you make a cone out of it, the 3D dimensional. So this is a cycloid. So he just printed this much. So that's a cycloid, and you just put a pendulum there. That's it. Simple. And now you put this, you extend this. When you're right here, its length has changed. Right? Its length has got smaller. So the simple idea is that the change due to the amplitude gets compensated by the change in length, but by the exact amount that they cancel out completely. So obviously he did a reverse engineering, not a very easy problem to solve, but he figured out that if you actually have a cycloid curve, then it completely cancels out. Remarkable, at least it does. And remember, that was a big technological leap, because it's almost like these days we have atomic clocks. When if you make a one order of accuracy better, you are almost probably in the high end of you probably get a if not anything, a prize probably. So in those days, clocks were just beginning to come up. Like this is 1680s. Galileo came up with this pendulum, using the idea of a pendulum to think for timekeeping. And since then, anything you want to do, this timekeeping is a big development. And anyone who makes a leap in that is a big deal. So PHYS got this idea, but very soon it was realized that there are easier ways to do this than make it. That's not the standard way of doing it. More, mechanical ways of achieving this thing. But this is accurate, theoretically accurate. I think that's the way to put it. At least I always find it impressive. Okay, so the quiz is tell something about cycloidal. And your homework will have not the cycloidal pendulum, the simple pendulum as a function of the amplitude. Okay, so that's your elliptic. integrals, what we what did we do? One thing we did was we did the derivative of e with respect to k. Right. And we showed that, I think this k minus e over something. Oops, where is it? Oh. So we showed e minus k divided by k small k. Great. So that was so we proved this in a few steps. Let's try to do the same thing for k, and we will see that it is going to be a little harder. So we'll have to introduce another integral. So let's try to find out what that is. So first of all, let's just do that in the standard way, right? Just take the derivative of this, right? Dk, and let's do that. So that's equal to k is down here. So that's 0 to pi by 2 d theta, and it goes up, so it is minus 1 by 2, right? So it's minus 1 by 2, and then in the denominator we get 1 minus k squared sine squared theta times, it's already minus 1 by 2 minus 1, so it's 3 by 2 or minus 3 by 2, which becomes 3 by 2 when you switch it to the denominator. And then I have to take the derivative of the argument of the square root with respect to k. So that's minus 2k. But then whatever is sitting in the coefficient also contributes. That's it. Derivative of the negative sign cancels out, 2 cancels out. So that's equal to k can come out 0 to pi by 2 d theta, and let me write this as sine square theta. I'm leaving some space, or I'll do the standard manipulation that we did last time too. Let me actually let me put this k back in there, and instead make it k squared and do this 1 over k. That's still the same, but then I can put a minus sign also there. That's a minus sign, and add a plus 1 to that and a minus 1. Reasonable? That's so that you can get this 1 minus k squared dependence, split this into 2. That's the idea. You'll see it in the next step if you're not able to see it already. Okay, so it's a trick there. So that's equal to, let me isolate this term, minus and a minus becomes plus, so that's 1 over k and 0 pi by 2 d theta. By 2, that's a minus sign, so let me put that minus explicitly. Oh no, that was plus, right? So minus and minus plus. And the second term is a minus. So minus of 1 over k, 0 pi by 2 d theta. 1 minus k square in the numerator, there is 1 minus k square sine square theta raised to 3 out in the denominator. So what is remaining is just 1 over sine square theta square root. Okay. And let me see if I'm getting apparently no, okay. Okay. This we identify as k, right? The elliptic integral of the first kind, but that's raised to 3/2. That's a new entity altogether. So let's define that to be something, and we'll process that. We will be able to express this in terms of the two, but for now, let's define this as a new integral. So let's call this pi of k divided by k minus of the elliptic integral of the first kind over k, right? Where I've introduced the function pi of k is equal to 0 to pi by 2 d theta over 1 minus okay. So this was e minus k. So this was pi minus k, where phi is a new integral. So what is pi of k? Next question that comes. Okay. So yeah. So to work on what pi of k is, let's go back to this e and actually try to work with this derivative of e, but in between we'll change our direction. So let me go back and do derivative of e with respect to k. Let's do derivative of e with respect to k. You already did this, but let's begin with this, and very quickly I will go in a different direction. When I take the derivative with respect to k, again it goes to the denominator, and that is a minus 2k. So let's see. So this is 0 to pi by 2 d theta, and that is a 1 by 2. And then this becomes 1 minus k squared sine squared theta. And this is minus 2k sine squared theta. And then we manipulated that, but I don't want to do that. Instead, I will do something else. So 2 cancels out. K can be brought out. And thank you. So minus k is gone, so there's a sine squared theta over 1 minus k squared. Okay, good. And here what we did last time was that we added and subtracted and recognized this. But we don't want to do that. Instead, what I'm going to do is I take 1 sine theta from that, so sine square theta. I take 1 sine theta from there and write that as a derivative of cosine theta. Okay. Is that okay? What is derivative of cosine theta?
Minus.
Minus, right? So I should change the sign. Good. Okay. So that's completely fine. And then play the trick of integration by parts, right? Why am I doing this? Because when I take the differentiation by parts, this will get raised to 3 by 2, and I'll be able to recognize the pi in there. So the idea is to get a pi there. And since I already know the result here, then if I can isolate the pi, I can get an expression for pi in terms of e or derivative of e and so on. Let's see. So So let's integrate by parts. Any questions at this stage? So let's integration by parts. So there's usually a boundary term. I think by now we've done it sufficient number of times. So take the overall derivative d by d theta of the whole thing, this and this, right? So this is sine theta over 1 minus k square sine square theta times sine theta. But that's not the whole story, because this now operates on this also. So I have to subtract things out, whatever extra has been put in. That's k times 0 to pi by 2 theta times, let's say, cosine theta here, and d by d theta times okay. This is a surface integral or a boundary integral in the sense that d theta cancels out. So this gets contribution only from theta equal to 0 and theta equal to pi by 2. At theta equal to 0, this goes to 0, right? This is 0, that's 0, that's 1, that's 1. So, but this is 0. Right? At theta equal to 0, it's immediately 0. No, nothing fishy there, because this is finite in the denominator, everything is okay. What about theta equal to pi by 2? That is 1. That is 1, but then k can go all the way unless you're really close to 1, you're okay. But this goes to 0. Right? So overall, this does not contribute at all at 0 and factor. So this is 0. So we only have this. So let's take the derivative there. It's equal to minus k. I can take the derivative of the numerator, 0 pi by 2 d theta, and I take the derivative of the numerator, that is sine theta, that becomes cosine theta, that becomes cosine square theta over 1 minus k square sine square theta. That's one term in there. And the second is when it hits the denominator, that we have to let's process that. So that's minus k 0 to pi by 2 theta, cosine theta and sine theta stay as it is. And when I take the differentiation, so this is minus half, so it's a minus half there. And this becomes raised to 3 over 2. It's 1 minus k square. And differentiate the argument, but this time it's in a differentiation with theta. So it is minus k square stays as it is. And we are differentiating sine square theta, so it is 2 sine theta, and then again a cosine theta. Right, so 2 cancels out, minus sign cancels out, so we have some simplifications. So that's equal to minus k and 0 to, oh, now I'm in the, no. So it's pi by 2 d theta, and let me make the let me write it in 2 steps. So this is cosine square 1 minus k square sine square theta. I've taken the minus sign out, so this is plus. 2 cancels out, and that is k squared sine square theta cosine square theta over 1 minus k squared. Just algebra, actually, most of what we're doing is just manipulating here and there, nothing tricky at all. Let's make the denominator the same concern.
The left term,
Huh?
should there be, in the denominator to the 1/2?
Oh, yeah, this one.
Yeah.
This one, correct?
Yeah.
Oh, yes, yes. Thank you, sorry. Yeah. Let's make the denominator the same. This is 1/2. If I multiply it by 1 minus k squared, the denominator gets common, so that's equal to minus k 0 to pi by 2 d theta, and cosine squared theta 1 minus k squared sine squared theta plus k squared whole thing divided by 1 minus k squared. Okay. And you notice that there is a cancellation. The sine squared cosine squared theta, there's a cancellation there. So this term cancels exactly this term. So there's a simplification. And in that sense, so I'll go to the other board, but let me write this down. So this is minus k 0 to pi by 2 in theta, and cosine squared theta, which I can write as 1 minus sine squared theta, I suppose. So this is 1 minus sine squared theta. Which, if you notice, has pi in it. So let me actually do one more step. That's equal to minus k times pi. Okay, first term is 1 over that, right? So it's pi integral. And the second one is plus k 0 to pi by 2 theta sine squared theta over 1 minus k squared. Are we good? Seems like, oh, this is, but we'll see that that's some cancellation there, and we'll get back to it. Okay.
So say I was doing this on my own, like what is the intuition of doing this sort of stuff? Just
Oh,
curious.
nothing. Okay, what is the intuition? Okay, best is to, I want to be able to write this in terms of E and K. There are two variables I want to be able to write that in there. And again, as I said, when you're doing a pendulum or when you're doing the circular wire, there is nothing deep in there. It's just that you're not able to solve it. But we know what is elliptic integral. If you can rewrite that integral in this form, then you're good enough. It's like saying that in the early days when you did not know the identities of sine and cosine, there is an algebraic expression which if you massage it sufficiently, it looks like sine function, and you identify that this is sine function.
Okay.
So yeah, we are trying to identify the circular wire will come in these pieces. That's the point. I think that's the best example I can give. So this is, I agree that this is mostly manipulations, which is not obvious at all. Yeah. Yeah. So, and yeah, I don't have an answer. Yeah. Okay.
No, I think just I think it was a good answer. You just rewriting in terms of E or K makes sense. Just
Yeah,
that's
so that's what it is. And actually, if you were to do this in the first, I remember when I was doing it for the first time, it seemed like I was going in circles like this pi to get this in terms of E and K. It was not obvious. At the same time, once you do it, it's obvious. Right? Like you said, like any other algebra, once you do it, oh, come on, there's no other way. But first time you go in circles a lot and it was not straightforward. Actually, Jordan, you are interested in stability problems, right? If you had to do stability problems, this shows up. Like this is one of the equations that shows up there. So yeah, fine. So these are standard manipulations in elliptic functions, whatever I'm doing so, or at least elementary manipulations. So maybe it is useful in that sense. Okay, so so what we have shown as of now is that the derivative of E with respect to K, which we already know in terms of E and K, right, is equal to minus K times the function phi and plus K. And actually, I want to manipulate this down. So this is plus K 0 to pi by 2 d theta. And we want to do the standard manipulation here. So this is 1 minus K squared. Notice I left space there. So that's plus K times this. So put a K there. In fact, put another K there. And divide it by K. And make a minus 1. Minus 1. Okay, so that I get this minus K squared from there. Then add a 1. And subtract. So that way, what I do get is minus K times pi. And this first term is again a pi, correct? But at this time it is pi of K, sorry, it's plus pi of K, minus, divided by K. And you have minus 1 over K, 0, pi by 2 theta. So there's a 1 minus K square in the numerator, square, well, 3 by 2 in the denominator. So what is left out is just 1 minus K square. Which we know is K. So we are almost there. So first let me remember the derivative of E, we know it, right? So E of K minus K over K. And what we have now is, right? So this is, what is it? So pi of K. 1 minus K square. Okay, so it's 1 minus K square over K if you want. And this one is minus so I probably jumped a few steps, but hopefully straightforward. Is that all good? Okay. You see a cancellation. This goes away. after it goes away, the denominator k also cancels. So I have an expression for pi in terms of e. And then we can go back and do your derivative of k with respect to k also, and we now have. So we know the function, we know the derivative with respect to k. Typically, it is also good to calculate the second derivative of e and k, but that goes through easily. Once you have all these identities, then it's just a matter of doing this. It comes within 3 steps. This is the only first derivatives are a little non-trivial. Second derivative comes almost trivially in 2-3 steps. So now I say we have a reasonable tools for using elliptic integrals. One is we should know the derivatives, we should know how they are related in terms of E and K, and the power series expansion, we shouldn't forget that. That's not really necessary, but whenever we get a result, we should be able to take some limits and check that it actually checks with what we know already. So in that sense, we need the power series expansion. Okay, so let's go back to our original problem then. That we want to do the circular wire. So this is circular wire. So that's your wire. Let's say there's a current I going through it. The radius of this wire is A, and that's your Z axis. And we said that the current density for this wire would be phi hat, or let me say this is phi hat prime. If it's in the xy plane, it is phi prime hat, and current I times Z, Z prime, okay? And rho prime minus A. That's your current density, and our vector potential at a point, observation point R, now arbitrary, can be close to the wire, far away from the wire, no conditions at all. It will find an expression everywhere. So that's equal to mu naught over 4 pi and cube r prime and g r prime. That's our superposition principle. Find r prime. That's all. We substitute this in here. R prime notice will be on the wire itself, but all the delta functions will contribute to that. So let's do this. Conditions. Okay. So that's mu naught over 4 pi integral of minus infinity to plus infinity z prime 0 to infinity rho prime d rho prime 0 to 2 pi d phi prime. Right, that's your 3 integrals. Phi prime now. Prime hat I delta of z prime of rho prime minus a, and what is that magnitude of the distance? This is in cylindrical coordinates, so this is z minus z prime square plus rho square plus rho prime square minus 2 rho prime times cosine of phi minus phi prime. We used this, we showed this in an earlier class, so let me do this again. And even in electrostatics, we used it in some form of geometry. two of the integrals are immediate, and the third integral, in fact, our whole goal then boils down to show that the third integral actually is an elliptic integral. That's all. So, but it will take some work. So let's do this actually horizontally. So that's equal to mu naught over 4 pi times I, and rho prime gets replaced with a, so that's I times a. And that is an integral of 0 to 2 pi d phi prime. Z prime gets equated to 0, rho prime gets equated to a. So this is phi prime divided by z square plus rho square plus a square. That's 2 rho a cosine phi minus phi prime. Roughly, you know this will be elliptic integral. Remember, your cosine function can be written as sine square function, like trigonometric identity. And these are all constants, so it's just a matter of arranging. But then there is cosine of phi prime and other things. So we have to manipulate those things to get this. Okay. Any questions at this stage? Okay, so let's solve vector potential A, or is equal to, let me explicitly, remember that z square plus rho square is r square. This is small I times A and 0. Phi prime is minus sine of phi prime I hat plus cosine of phi prime j hat. Divided by, this is r square, so I'm mixing the cylindrical and radial, spherical coordinates. For the observation point, I'm using spherical. For source, I'm using cylindrical. A square. And that's because this is the standard expression. Let's do something straightforward. Let's try to, like, we would like this to be having only the integral parameter, right? Let's try to get this phi away from here. So we would say, let's substitute, right? So let's substitute phi minus phi prime, or actually phi prime minus phi. Like this can be written as phi. So sine doesn't, it's not sensitive to sine. So it's phi prime minus phi is equal to phi double prime, and d phi prime is equal to d phi double prime. So when phi prime is equal to 0, phi double prime is minus phi, and when phi prime is equal to 2 phi, so this is 2 phi minus phi. D phi prime is d phi double prime, and now the numerator changes to minus sine of phi prime is phi double prime plus phi, that direction, plus cosine of phi double prime plus phi. And so basically we have moved the phi dependence from the denominator to the numerator. That's all we did. Sine of phi double prime. Right, if we were to pull this r plus a square out, there will be a 1 minus a coefficient, and cosine of phi prime has 1 minus sine square relation. So you sort of very vaguely see the elliptic integral, but then all the limits doesn't make sense. So let's keep pushing this. So let's expand this out. So there's some. First of all, before doing anything, these are periodic functions. This whole thing can be shown to be periodic. And you're going from, instead of 0 to 2 pi, if you go from minus pi to 2 pi minus pi, that's still a complete period. And integral has to do with sum. It doesn't matter in what order you sum. First you do this, or you start from 0, it doesn't matter. So this I can immediately still replace it with 0 to 2 pi. So that's perfectly fine. So we have naught 4 pi times I times A, and 0 to 2 pi phi double prime. Expand this whole thing out. So this is minus sine phi double prime cosine phi, and there's again another phi hat, the minus cosine of phi double prime sine of phi hat. Then there is in j hat direction, there is plus cosine of phi double prime times cosine of phi, in the j hat direction, minus of sine of phi dot and sine of phi and the j hat direction. And that is r square plus a square okay. Let me group this separately. Notice that if I were to take sine phi common, let me rewrite this in second step. Another step. Sorry, it says algebra, but I think that's only. Okay, I'm going to group these two together and these two together, sine phi together, and cosine phi together. When I group the minus sine phi double prime, whatever is remaining is cosine phi and sine phi in the I hat and j hat. That's nothing but rho prime, rho hat. But now observation rho. Earlier we started from this source of phi prime hat, but now we're getting something. And this one I want to write this as plus cosine phi double prime. These two terms is nothing but phi prime. No prime. This is not prime, sorry, phi hat, but no prime. Right. So that's
d5 double prime.
yes. Okay, the integral is double. Thank you. Okay. Okay. So this can come out, right? These are now source variables. I can come out. So there are two integrals here. And if I can do that, then I'm good. Right? So I'm going to write this as there's two quantities. So there is minus rho hat, the first one, not over 4 pi I times a 0 to pi prime. That's the first piece. The second piece pi hat again comes out. The first pi hat source variable. And that's the sign. Okay, at this stage, let's pause for a moment and ask, what do we expect? Remember, this is the electric potential due to a magnetic potential due to a current carrying loop. What should it look like? Maybe recall. Yeah, any comments?
Should be like in the direction of Z, like this.
The direction of Z.
Right.
Let's go back and think of a infinitely long wire, current carrying wire of I.
Oh, yeah.
What's the magnetic field associated with this? Circular, right? I had that. What is the magnetic potential associated with this?
Parallel.
Parallel, right? Very good. And notice it's parallel to the current, usually the direction of current. If the direction is uniform, then it's steady, let us say, then that decides that. So magnetic field is circular, but vector potential actually is in the z hat direction. So in that spirit, we are now talking about a loop of wire, right? This is a loop of wire, current carrying wire. What do you expect should be the direction of A, maybe?
Tangent.
Like it should be loops, that's what, and that is a correct statement, even if it is not very obvious. It's a kind of a very broad analogy I'm giving. But another way of looking at it, this is that the contribution at any given R prime gets additions from all these J's, right? All these J's have to add up. Yeah, that's no. Let me not try to convince that. Let's say that. Is there any other argument I can make to that should be circular? E should be circular. Because del cross A has to be B. Right? So
Is it circular or is A tangent to the curve at every point? Like
no, it is circular, like circular in the sense it's in the direction of phi hat. So my point is that, okay, what I'm trying to point out is that this is the only term that should survive, and on physical grounds, this should not survive. This whole thing should collapse right away. But let's not use that. So, but then we should be able to show that this integral is actually 0. Right? So we'll show first thing we'll show is that this is 0. Right? That will come out to be 0. And the second is that this actually can be switched over to the elliptic integral. It's not very obvious, right? But again, remember cosine phi, the idea is that what is the connection between sine? So sinus 1 minus cosine 2 theta is 2 sine square theta, right? Isn't that right? So we use this to write this in terms of sine square theta. And remember, sine square theta is what elliptic integral is. That will change our integral from 0 to 2 pi. Instead of 0 to 2 pi, it will go from 0 to pi. But still, we have to make it to 0 to pi by 2. So there will be another symmetry we'll invoke. So those are the manipulations we will make, and all this we'll get into. Not a single elliptic integral. It will be a combination of elliptic integral. That's the non-trivial part, like that. Like the perimeter of an ellipse and pendulum and all comes out right away, either the first elliptic integral or the second. Here it will be a huge combination of them. But that's what we want to do. So hopefully that gives you a small feel for what's going on. And let me today start by first showing that this integral is 0, and then we will stop and then come back and process this integral next time. I also have extra time, right? You guys promised that I take, or you guys offered, I shouldn't say, I promised you guys offered that I could take extra time. So let's see how far we can go. Yeah. Okay, any questions at this stage?
You said you were taking the source variable out.
Yes.
Is it the source? Usually the prime variables are the source.
Oh, did I say source? No, I meant to say observer variables out.
Yeah.
Because these are observer variables, right? No primes there.
Yeah.
Yeah, if it is source, I cannot take it out
Right,
because,
right.
maybe I spoke wrong.
I figured so. I just wanted to.
Yeah, good point. Yeah. So we started with all this phi prime hat, but we manipulated it and switched it over to this. We started with the source variables prime, and then we manipulated it so that the observer variables can be brought out. All the directions are in the observable variables. That's the manipulation done in a sense. Okay, so let's try this integral. It should be whenever it's 0, most probably there is a symmetry in there, right? So let's try to see that 0 to pi and pi to 2 pi probably is the same. That's typically how it works, or probably that's how it works. I'm not sure, because at least in this case, that symmetry is not there. We have to go into 4 pieces and do this. So let's see if that works. I don't remember exactly how we do that. Okay, so let me switch over to here. So let's do this integral alone, right? So move this. So let's just take that integral and let's just call that I1. So that's 0 to 2 pi and d phi prime. Sine square, no, sine. Okay.
I have a suggestion.
Yes, yeah. Suggestion.
So the integrand is periodic with period 2 pi,
Yes.
right?
Uh-huh.
So from 0 to 2 pi should be equal to from
2 pi to 0.
or negative pi to pi.
Negative pi to pi. Okay, yeah, sure.
And the integrand is an odd function since the numerator is odd and the denominator is even. So
it's immediately then comes out. Okay, good. So I think what Luke is suggesting is that this is a periodic function, and so it is that obvious? Yeah, it is, right, periodic, yeah, it is, sorry, yeah, it is periodic function, but I was thinking, is it symmetric or not, but we are not assuming symmetry, we are going to show that, right, yeah. So that's minus pi to pi. So if it's a periodic function, I can go from 0 to pi, 2 pi, or minus pi. Okay, that's, I think, a good thought. And so there is two integrals then, 0 to pi. We can use the anti-symmetry property now, but let's do that explicitly here. And this is minus pi to 0. This seems to be a good idea. Maybe we can try the same thing on the other one also. Useful. Okay. In the second integral, substitute, we want the even odd feature in here, right? Which is actually trivial, right? It's immediately clear because when I replace phi double prime with minus, let's just do phi double prime, substitute this to phi triple prime. Only in the second piece, first piece, I keep it as it is. So that's equal to, when it is minus pi, this is pi, and when it is 0, that's 0, that's equal to minus d phi triple prime, and this is sine of minus triple prime, and this is equal to r square plus a square minus 2 rho a. This is it. There's already a minus sign here. There is a minus sign coming from that differentiation. And if I were to flip this integral from 0 to pi, that gives me a third minus sign. So 3 minus signs gives me 1. That is 0 pi d phi triple prime sine phi triple prime. Which of course you don't have to do this, as you pointed out. It is clear right away there that that's an odd function, so that cannot contribute. So that's 0, right? So that's equal to 0. Okay. Nice. So we are left out with this integral, and let's manipulate that. So that's I2. Can I erase this? I2 is integral 0 to pi d phi double prime cosine of phi double prime r square plus a square minus 2 rho a cosine phi. Again, I feel that there must be shorter ways of doing this, but maybe let's try whatever you are doing. Let's do this minus pi. So this is the same as minus pi to pi. Correct?
Which is the same as 2 times 0 to pi?
Yes, because
The integrand is even.
integrand is even, right? Immediately. Yeah.
I don't know if that helps though.
Yeah. So this is equal to exactly do the same thing here. The only difference will be that this minus sign will not show up. So this will become plus. So it will be exactly the same. So this is equal to 2 times 0 to pi. Any questions on that, by the way? It's clear. Let me know. I jumped a step. So what do I want? Application. Yeah, I think from that point on. Minus. Oh, there's a problem. Why did this change sign? I got a minus sign here. Oh. Probably it's the same. This is okay. There's nothing wrong in this, right? What about this? Because when I substitute this cosine phi, 1 minus k squared. Yeah, let's substitute this right away. I think I'm having issues with this minus sign here and an overall sign, but we want our elliptic, right? We might have to retrace our steps a little. So cosine phi double prime is equal to, what's our identity? So 1 minus this, so it is 1 minus 2 sine square phi prime over 2, correct? Isn't that the relation? How do you do that? So it's cosine square minus sine square, so that's the same as, this is cosine of 2 phi by 2, right? So that's cosine square phi double prime over 2 minus sine square phi double prime over 2, right? So I replace this, so that's correct. Okay, so let's, if I were to replace that, what do I get? Does that help me? So that's 1 minus 2 square phi. Because then I will make it 0 to pi by 2. It's r square plus a square minus 2 rho a times 1 . That's okay. And I don't like that, I guess. I think that's not wrong, but yeah, I think the catch there is that the sine square comes with the plus sign. Right? And our elliptic integrals have this minus sign in front of them. So let's go back and see that this actually is also can be rewritten. How can we change the sign? We have a substitute phi prime equal to pi minus phi or something, right? If I were to move this by pi. So let's do that. So retracing steps. Sorry. So I go back here. I don't want to do this. Okay, I don't want to do this, but instead I want to do, I want to substitute, right? Cosine of something plus pi is actually, so what if I substitute phi double prime is equal to pi plus, or pi minus actually, phi minus phi triple prime. Okay, so that way when it is pi, this will become minus, and when it is 0, that will become pi. I think there is a connection there, so we'll see what it is. So this is d phi double prime is equal to minus d phi triple prime, and this is equal to 2 times, when it is phi double prime is 0, this is phi triple prime, be careful, so it's pi minus phi double prime, so that's pi, right? Phi double prime is 0, this is pi. And when it is equal to pi, that's equal to 0. Right, so this is minus d phi triple prime. And cosine of phi double prime is cosine of pi minus phi triple prime divided by r square plus a square minus 2 rho a times cosine of pi minus phi triple prime. With me? Okay. Did I lose any of this? Cosine of pi minus an angle is minus of cosine of that same angle. Right? It's in the second quadrant. So that's minus. This is minus, 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 and I will flip this. So this gives me a minus 2 times 0 to pi d phi triple prime cosine of phi triple prime divided by r square plus a square minus 2, plus 2 rho a, which is what I was suggesting, right, or what I was looking into my notes and seeing. So it's changed sign, so the here it changed sign and this it changed sign. Right? That's the two things that happen. So almost there. So I can take 10 more minutes, right? Please. Yeah, okay. So then I can finish this. I think we can get this This is very good. Like otherwise, this would have gone into 2 or more lectures. Okay. So if I substitute this in the expression for, can I switch over to the right? They can follow. Okay. So A of R is equal to the minus 2a, so that's pi hat times mu naught over 4 pi times minus 2ai. So the minus sign there, and the whole thing is pretty much the same, except now it is 0 to pi. Oh, I should have done the sine square theta there itself. Right? 0 to pi. Plus 2a rho times cosine by triple prime. Almost there. Substitute that identity we had, cosine of phi triple prime is equal to 1 minus 2 sine square phi triple prime over 2. So that's equal to minus 2a pi. And this is 0 pi d phi. Cosine phi is 1 minus 2 and 1 minus, so this is okay. Substitute phi prime triple prime over 2 as a new angle, theta we will call it, because we want to use that go at least to some place instead of 4 primes. That's what it was. Okay.
Yeah, I thought you were gonna say quadruple prime.
Yeah. Okay, can I keep going horizontally then? Michael and Jordan and Olivia, you guys following me, right?
Yeah, you're good. You can keep
Yeah.
going.
I can keep going, right? You can see
Yep.
everything. This is okay. So I'm substituting 5 triple prime over 2 the theta. So d phi triple prime is equal to 2 times d theta. So when phi triple prime is 0, theta is 0. When phi triple prime is phi, this is 0 to pi by 2. So that's equal to phi hat naught over 4 pi minus 2 ai times 0 to pi by 2. D phi triple prime is 2 times d theta. And then you have 1 minus 2 sine square theta. And this is the first two terms is r plus, no, it's not there. This is actually, there's a rho square here, right? The rho square plus z square. Let's leave it alone. Let's not manipulate that. Too many things at the same time. Okay, so that's a constant and minus 4a rho sine square here. You can at least identify our k square, right? If I pull this out, that is my k square. That's coming up. How much more time can I take?
I'm fine with whatever you need.
Rob, you had some office hours?
I have tutoring that I could give until like 5 after, unfortunately, but I can watch the video if you want to finish.
Yeah, because if you allow me to go about 10 minutes, it's just a few steps there, but I think it is 2 steps, but then it might come up. So if you allow me 10 minutes, like.
Because I can kind of see where you're going with it.
Yeah.
So I think that if I just
Yeah.
watch,
It should be
I'm gonna
okay.
write that down and I'm gonna go see if the.
Yeah. I'll take 10 more minutes and then we'll be done and then we'll have caught up with everything that this will be smooth. Okay. So, okay, so then I can go back and erase some properly. Okay, so our A is equal to phi hat mu naught over 4 pi, and that was a minus 2ai times a 2 there, so that is a minus 4ai. Let me do the second steps. Thanks, Rob.
No problem.
That's 0 to pi by 2. Yeah, 1 minus 2 sine square theta divided by r square plus a square let's define k square to be is 4a rho divided by r square plus a square plus 2a rho. So I pull this out, so I can write my a of r as I hat mu naught over 4 pi times, let me pull this out. So I have minus 4ai divided by r square plus a square square root of that. And that rest of the integral is can be written in terms of k square.
Do we still need the 4a row?
Oh, 4a rho.
Sorry.
What?
Did I miss?
What? Oh,
So the numerator of k squared?
so here.
Oh, yeah, okay, yep.
Right.
I missed.
So I pulled this out. So
Yep,
this,
yeah,
I think it's okay.
yeah, I'm good. Thank you.
And I can check it. Yeah, it's okay. Yeah, from this point on, it's just this integral, right? So we just have to check that what is the elliptic feature of this integral. So let's do that. Yeah, so let's do that yourself. Let me put that as minus outside 4ai. By the way, r square is also z, right? So this also can be written as, I mean, it's sort of straightforward, plus rho plus a, the whole square. Nothing special about it, but just often you will see this written in this form also. That's the same thing. Let's open a bracket here. So this is 1 divided by this, that's a k. Right? Immediately we have a k there. And minus of, I want to again manipulate that. So this is minus of 0 to pi by 2 of d theta, and you have minus 2 sine square theta divided by 1 minus k square sine square theta, but I want to keep it as plus. That's correct. So pull the 2 out. Pull the 2 out. Introduce a k square and divide by a k square. Same idea that we have been doing all through. There is a 1, add a plus 1, and then add a minus 1. And then close it. That's equal to minus pi hat e naught 4 pi 4 a I. Oh, am I written that? Plus okay. The minus 1, that's again a k. So this is minus 2 times k, but this time divided by k square. And the next one is square root cancels out. So it is plus 2 times e of k over k squared. That's it. That's your expression for the magnetic potential. Very not at all intuitive or anything, but very useful in the sense this is your magnet, right? This is a circular wire in a lab. It is very relevant, right? So this is an exact expression. How much ever close you get, you can verify this as much as you want. But this is again a vector potential. There's a similar calculation you can go through for magnetic field, or take the curl of this and go back. I won't do that here in the classroom, but in the homework I will give you, at least I will go through the whole steps and make you guys go through a few of the intermediate steps. But what we have to do is take some limits. That is much more nicer. Otherwise, this is just an expression. It is not very, does not have much insight. As Jordan was complaining right at the beginning, right? Why are we doing this? But I feel it is important to do it because this is one complicated or one simple example in a lab. In theory, it is pretty hard.
No, that was helpful.
Yeah.
I have one question.
Yeah.
So just like at face value, it looks like A of R is going to be a minus phi hat. Is that true?
Put the minus inside. I was just looking at my friend. Put the minus inside.
Okay, so
Write this as k 2 minus k squared. So let me write that.
okay, yeah. I was just wondering because it looks like there could be lots of places for other minus signs to come in.
Yeah.
Okay.
It all fits in. That's what we will take some limits now. But that we should do it next time.
Yeah.
We should do that here. I think I'm still looking here. So this is best written as over k. Oh, so it's k of k. So it's 2 minus k squared over k squared and minus of e of k. Like we will verify that for small k somehow we can get some reasonable answers on it. And we know what the a is supposed to be on the axis, for example, for what features we can check. Okay, good. Thank you guys, because you guys allowed me to go far. So I think this sort of catches up with whatever we missed. This could take easily 2 or even more when you split this.
Yeah, no problem. Works for me. And it's actually helpful to see it all in a row instead of like piecing the puzzle.
Yeah, even from the student's perspective, probably that is good. But for Aliyah, I don't know, yes, his kids and families are longer time.
I barely hear you. So noisy.
We cannot hear you, sorry. Aliyah?
Me too. I barely hear you because my background is noisy.
You were really feeble.
She said she can barely hear you too because her background is noisy.
Oh, I see. But hopefully the recording comes out okay.
Yes.
Okay, thanks again. Yeah.
So in the future, whenever you see, since we've already determined, the direction that A is always in the direction of the current, so it's in a loop in this case. When we see pieces that come out that aren't also a part of that loop, the direction of that loop, you just say that they're equal to 0, basically, because A is not related to rho hat, but it's related to phi hat.
Repeat that. I think the volume is a little low. Let me increase the volume here. Go ahead.
I was just saying, like, because we know that that the magnetic vector potential is in the direction of the current. When we have terms like this in the future, instead of showing that it's equal to 0 always, we can just say.
No, it is not always true. It is not always true. These are special cases. You can imagine, right? Suppose there were one loop and another loop not in the same plane. Then this will get jumbled up very quickly. These are very symmetric situations have these features, but not always. That's why to back my statement, I was even in this case, probably it's not very trivial to see that it has to be that. So we had to show that that integral is actually 0. Yeah. Good. Yeah. Okay, Sharon. Shall I disconnect?